Okay, so let's put the orbital configuration method that we just learned into use. Okay, so we start by an example of the chlorine electronic configuration. So I have written it down as 1s2, 2s2, 2p6, 3s2, 3p5, which you can always go back to this and consider this while you're filling up the electronic configuration. So when you use this, you will get an electronic configuration which looks like this. Now you can convert this into K, L, M, the orbit style, but I would just leave it because that's too easy and you guys already know that. Okay, so let's see visually how the electrons are getting filled in these different orbitals, or how the guests are starting to pour in into the hotel rooms. Now, one thing that is to be noted here is that if you have a room in here, the electrons will have to have different spins. Now, what do we mean by spins? We'll be looking in a concept called the quantum numbers, but for now, just assume, just remember that if you have we represent an electron with this half arrow things. Okay, so if you have an electron which is represented by this half arrow towards up, we can not have an electron which is also pointing towards up. This is not possible. So if you have an electron which is filling above, like up, in a single room, you can only have an electron which has a different spin. So this is a different spin electron, and this is a different type of an electron with a different spin. We represent it by using the numbers plus half and minus half, but this is a quantum number concept which we will be studying ahead. For now, just remember that, okay, you cannot have two electrons which can be facing upward. One has to face upward, the other has to face downward in a single room, because a single room can only have two occupancy, right? Okay, so what happens when you have 1s2? So first electron goes in here, the second goes in here. 2s2, similar. Now what happens when you have 2p6? Now let's assume that you have already 4 electrons taken care of in here. The 5th electron comes, so the 5th one goes in here. When the 6th electron comes, where do you think the 6th electron will go? Will it come in here and make a pair with this electron, or will it try and occupy this room? Now, I think if I am the guest in here, I am the 6th one, I would not want to pair up in here, given that in the same suite, we have a different room which is completely vacant, right? So the 6th electron will go here. 7th, they'll go in here. It's the same suite, it's a different room, right? Now, what happens if you have, now you have 4 plus the 7 electrons taken care of. What happens to the 8th electron when it comes? Now you have to pair, because if you don't pair in here, then you have to shift the suite. You have to move to a farther suite. That's not favorable. Let's keep the suite same and we start pairing, okay? 3s2, similar. The similar situation happens in here. Okay, I have written px, py, pz is just the names of the different rooms we have. We have a p-type suite. The 3 rooms in P are called px, py, pz. We'll understand why that happens later. Okay, similar, like this is governed by the quantum numbers. Okay, now what happens to the p5? So the first electron goes in here, the second does not go in here. This goes in here because it's the same suite, it's a different room. It's better to not share, okay, in the same suite when we have a chance of not sharing. Okay, the next one comes in here and the last one goes in here. So this is how you show the number of electrons of the chlorine atom and how they are distributed in the different orbitals. So this is how you do it. So I suggest that you go through you try and like draw these box diagrams, as we call it, for the different atoms. So you can do this for all the different atoms in your periodic table, and then check whether you're getting these in the right way or not. Okay, so I suggest that like you should practice writing these box diagrams an electronic configuration. Now, as I said before, that writing these different electronic configuration will help us determine many different kinds of properties of the atoms or the ions that we have. Now, an example is why Cl- is a stable species. Like you might have heard the chloride ion, which is a Cl- ion. Now, doesn't this question come to mind? Why only Cl- exist? Why does Cl plus doesn't exist? Why does Cl2- doesn't exist? Why does Cl atom doesn't just roam around? Why do we need to have a Cl-? Now, we need to understand the concept of stability to understand this, okay? Now, to understand the concept of stability, we bring in the concept of stability of these orbitals. Now, in order to understand the stability of these species, we have to understand what are the configurations, what are the types of electronic configurations that actually are stable. Okay, the most stable configuration is a full filled configuration. Now, if your room is fully filled, that's a stable configuration, okay? That's fine, okay, full filled, you have all the rooms occupied, that's a very good stable configuration. The next best is a half filled. So each of the rooms, if they have half, so for example, if this is the P suite, this is a half filled orbital. This is a half filled because the total capacity is 6 and we have 3 and each one of these have single electron. So this is a half filled. How do you make it full filled? You just pair them up. So this becomes a full filled orbital. So this full filled is stable, more stable than half filled. Now, what is even less stable than the half filled? Any partial filled. So what's an example of a partial filled? This is an example of a partial filled orbital. This is an example of a partial. This is half filled. This again becomes a partial, fully filled orbital, okay? So we now have to keep in mind that, okay, full filled orbitals are more stable than half filled, which are more stable than the partial. Why? Again, quantum numbers and things like that. We'll try and understand them. But for now, let's try and understand how this thing will help us understand the electronic configurations. Now, why do we have a Cl- which is stable? And keep in mind the concept of the ions, right? Now, the ions tell us that Cl- is an anion. Why? Because it has a negative charge. How did it get the negative charge? It must have an extra electron. Now, my question is, how does an extra electron in the chlorine atom make it stable? Let's see what happens when this chlorine atom gets an extra electron. What do you think happens? You get an extra electron, and this electron will try and go to the outermost, right? What is in here? We have a 3p5, okay? So as we have said before, any electron that is exchanged is from the valence, okay? We'll see this example more clearly, in which it does not matter if the last shell that you're filling is the outermost or not. For example, the last shell that was being filled in here was a 6p2. Okay, this is not a great example because the last shell and the outermost shell filling is 6p. So any electron that is going to come in or get out is from the 6p2. But if we take the example of chromium or copper, we'll be able to see what I mean by the outermost shell and the last one getting filled, okay? For here, the outermost and the last one is both 3p5. So, and any extra electron that comes in to a chlorine atom is going to be filled in here, okay? Now, what just happened? You went from a partially filled orbital to a fully filled orbital. And that is why a chloride is more stable than the chlorine. And that is why you have a Cl minus ion, which is more stable than any other. If you have a Cl plus, what would have happened? If you had a Cl plus, this all would have remained constant. It's the same. The last one would have gone to this. It had 3p5, now it has 3p4. Did it make it stable? No. The Cl plus did not make it stable. So this is not going to help it become more stable, right? On top of that, it is giving you a positive charge. Charges are not stable anyway. So if you're getting a charge, you would want to have a stable configuration, right? At least you're getting a charge, you're getting a stable configuration if you have a minus. You don't want to get a Cl plus or to Cl2 plus in order to have a half fill, right? It doesn't make sense. So if you just get a 1 electron and then you make you get your shells fully filled, that's a smart move, and that is why you have a chloride ion which is stable. Okay, now let's take an example of the Na. So for Na you have 1s2, 2s2, 2p6 and 3s1. So you have 10 plus 1, 11 electrons, 11 in here. Now if you arrange this, so this is the box diagram. So you know the box diagram now. So in here. Now, Na plus, just when Na plus is formed from Na, what happens is this electron is lost. So if you just remove this electron, you are getting a fully filled electronic configuration in here. And that is why Na plus is stable. You don't want to go to Na2 plus, because if you go 2 plus, this fully filled will then lose 1 electron and then become partially filled. So you don't want that, right? So this becomes Na plus, and that's why it becomes stable. It could have also, so now your question might be, what if you get an Na minus, then also this becomes stable? Yes, it looks like that, but please remember, then you have a 3p in here too. So unnecessarily you are occupying these orbitals. You don't want that. You want to be as close to the nucleus, as close to the Olympic Stadium as possible, right? And that is why Na minus would have added this, but then this whole 3 orbit is getting 2 electrons, and it is much better to just lose this and get a stable electronic configuration in here. Similarly, for oxygen, if we have, so we have 8, so you have 1s2, 2s2, 2p4. So in here, these two remains the same. So you have a 2p4 which looks something like this. Now how will you make this stable? You add 2 electrons to this and get this whole thing stabilized, right? You fully filled the entire orbital and the entire orbit. So you get 2 electrons in here and you get this complete thing fully filled, and that is why O minus 2 is stable, and that is why O minus 2 is stable and not O minus 1. If you just had 1, it would still be in a partially filled state. So that wouldn't solve the problem, right? And that is the reason you have minus 2. You don't have plus 2, because if you had plus 2, then again you would have gone from this to this, right? In which you have only 2 electrons in here. So that wouldn't solve your problem either. So that the best way to get this thing to stabilize is getting a minus 2 in here, and that is the reason we have a O minus 2. Okay? Okay. So let's take an example of the chromium element in here. Chromium has an atomic weight of 24, so let's try and arrange the 24 electrons. Okay? So we start with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now, how many electrons is being taken care of? This is 10, 12, 18, 20. Now we have 4 left, okay? So, 4. Now, here is a case in which the last filled is not equal to the outermost. This 4 is the outermost. Why? Because this is the 4th hotel. 4th hotel is outermost, right? It is below this. It is the filling order is 4s first and 3d after that. But what is the outermost? 4s is the outermost. This you can understand by assuming that, okay, now why is 3d more favored than why is 4s more favored than 3d? Again, we'll come to the concept of quantum numbers, in which we will be able to find out why 3d is being why 4s is being favored over 3d. So we'll be dealing with that after this, but in here you please understand that 4s is the outermost orbital, but the last filled orbital is 3d. Now, let's try and draw, let's see what happens in here. So you have a 4s, which is outer, so I'm drawing the 4s in here, and the 3d in here, and 3d has 5. The 3D suite has 5 rooms, okay? Now, you have a 3D4 and a 4s2, right? So this one filled first, and then you have this. Now tell me, does this look stable to you? This has a 3D configuration, is half filled. This is full filled. So is there a way to stabilize this? An easier way to stabilize this would be if this electron from here comes in and gets in here, right? So this whole thing becomes half filled. Previously this one was full filled, but this partial. The partial is like making this whole thing very unstable. Now in here, if we have two half-filled orbitals, this is much more stabler configuration, and therefore for chromium, 4s2 3d4 is not the right configuration. The actual configuration is 4s1 3d5, and you have this configuration. So if you convert this into KLM, the normal configuration, the K takes 2, L takes 6, 3 takes 2 plus 6, 8 plus 13, and N takes 1. So the configuration of chromium is 2, 8. 6 plus 2, 8. 2, 8, 13, and 1, which would have been hard to understand just by the concept of orbits, right? Why is this 2, 8, 13, 1? Why is it not 2, 8, 8, 6 or something like that, right? Now, we cannot explain that with the concept of orbits, but we can explain the configuration of chromium with the SPDF system, the orbital system. Now, I would encourage you to try and write down the electronic configuration of copper, which follows somewhat of a similar rule in here, and when you understand this correctly, you'll be able to use the same concept to write the configuration of copper in here, okay? So super helpful, the configuration of chromium and copper, which can be explained by this concept of half-filled being more stable than the full-filled orbital, okay? Now, let's take another example of iron, which has an which have an atomic number of 26. Let's try and write this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So I think that takes care. So this is 10, 18, 20, 26. Okay. So this is the configuration of iron, no problem there. Please understand that this is the outermost orbital. Now, even though the last electron entered into the d orbital, now if you want to exchange electrons, you want to take out electrons, 3d is not going to give out electrons. Why? Because 4s is the outermost orbital. So any orbital which is the outermost is responsible for the exchange of electrons. Now, let's assume that you want to write the configuration of Fe2+. Now you know Fe2+ means that you have lost 2 electrons. Now tell me, where from will you be losing the 2 electrons? You're right, you will be losing the 2 electrons from the 4s2. Therefore, the electronic configuration of Fe2+ becomes right. Now, this becomes the electronic configuration of Fe2+ because the 2 electrons are lost from 4s2. Okay. Now, what happens when you have Fe3+? Now, you might have heard it somewhere, read it somewhere that iron has two charged states, Fe2+ and Fe3+. Why is that? Why does iron have 2 states? Why after getting Fe2+, this would want to go into an Fe3 state? The answer is very simple. In here you see that the 3d which is now left is partially filled, right? So if we try and draw this, you have 6 electrons in the outermost. Now this wants to be stable. How will it become stable? This partially filled needs to go to a half filled, right? Filling it completely would be a gigantic task, right? Now, but removing 1 is easy. So you just remove this. So this becomes a 3d5 and this whole thing becomes stable. Therefore, Fe3+ is more stable than Fe2+. Why? Because of this. Because the d orbital in Fe3+ is half filled, which makes it more stable than Fe2+. So this is how we try and make use of the electronic configuration that we learned, the orbital configuration that we learned, to understand the different concepts of chemistry. I would encourage you to please try the electronic configuration of copper, because this will take similar concept from this chromium one, and in general try and draw the electronic configuration, write down the box diagrams, draw the configurations, and try and understand why you have Na+, why do you have Mg2+, what happens when you write down the configuration of sodium and write just a 1+, and try and convince yourself why is the Mg2+ more stable than Mg+, based on the things that we have learned. Okay, this is a very strong concept, and I hope you guys have understood this. So putting up our understanding these basic concepts will now equip us in a better way to understand chemistry in a more clearer fashion. Thank you.